Okay, actually we learned something small about them, but we've not gone into details. So we look at how we can define our operators and how we use them to operate on functions. So operators normally act on functions, not values. So when you take an operator, operate on a numerical value, it still give you that number. So it is always having effect on a function. Okay, so we can write this just as this example that you are seeing on the screen. So the H is what we call the Hamiltonian operator, and then the psi is the wave function as usual. So H cap is the Hamiltonian operator. Hamiltonian operator. And it is normally defined as this: minus H squared. Then you have D squared. Then you have the wave function, or if you don't want to bring the wave function, since I'm not writing the wave function, so this one will be over 2m. So d square over dx square. So this one is telling us that when you look at the numerator, it is waiting for something to operate on, because you don't have the something like the x in mathematical form. You should have d of something before the dx. So if you have d dx, it means that there is something to be written here to make your expression complete. So when we define the Hamiltonian operator like this, it means that it have to operate on a function. So when I bring my psi here, the wave function here, then it will now give me my h of psi, and that will be the h operator. But in classical mechanics, we know that the Hamiltonian is nothing but the sum of the kinetic energy and then the potential energy. So that is the mechanical energy. So you can also write the full version. So this would be V as a function of x, because I'm using x, so it means that my potential energy is along the x direction. Okay, so this would be your definition for the Hamiltonian operator. Now, if I want to attach the wave function to it, so I will now have my psi cap of h cap of psi will now be the whole of this. So this will be equals to, in a bracket, I will have minus h squared, the square over 2m, the x squared, then plus v as a function of x, that everything will now be written in terms of psi. So I can now expand this by multiply through the wave function inside the bracket. So when I do that in the next slide, I'm going to now have my h cap of psi now be equals to minus h squared. Then I have the second differential of the wave function respect to x, okay, then plus v as a function of x, then psi as a function of the psi is also a function of x, and then time. Okay, you can put that one, but if you see it in a short form, I know that it depends on position and then time. Okay, so this side, the right hand side of this, is what we call the mechanical energy. So when you look at the Schrödinger equation is written as this: E of psi. We will see this equation later on as we progress. So what the Schrödinger equation is saying is that when you take the Hamiltonian operator operated on the wave function, you will get a certain number which is not a function, then multiply by the function that you are operating on, and this is what we always call the eigenvalue. The eigenvalue, and this is what we term as the eigenfunction or the wave function. So the eigenfunction, so the normal function that you know. Now I explained this wave function as in physical meaning. It doesn't have any physical meaning, but what it tells us is that it only gives us an information about finding the probability of an electron that is executing a one-dimensional harmonic motion. So it's a probabilistic statement. So it tells us the probability of finding an electron if that electron is moving within a confined space. Okay. So it's just about giving us the mass information or the mathematical information about that. So we can also have our kinetic energy operator. Since we know that mechanical energy is equals to kinetic energy plus potential energy, so we can write our operator in terms of the kinetic energy. So T is the kinetic energy operator, kinetic energy operator, and this is also defined as this. The kinetic energy operator is defined as the h bar square over your 2m, and then this is the d square over the x square. So this is an operator. So when it acts on any other function, then you bring it. It can be the wave function, it can be a variable. Okay. Now, you and I know from the classical mechanics that we can transform kinetic energy to be dependent on momentum. So that is where these things are coming in. So when you know the momentum operator, so P cap, which is the momentum operator, let me write that before I define it. So P cap will also be the momentum operator. And this is defined as this. So that will give us the minus h bar, then we have d dx. So this is how we also define the momentum operator. And where you are seeing the in the kinetic energy expression, because from the classical mechanics, we know that kinetic energy is equals to P square over 2m, if you recall this. So when you know the definition of the P operator, then you can actually get the operator for the kinetic energy. And once you know the kinetic energy operator, you can also get the operator for the Hamiltonian, which is the sum of the potential and the kinetic energy. Now we also have our position operator. So when we see x cap, is what we call the position operator. And this one defined as x. So when you take the x operator operate on another variable, you still get a linear value. You get a number, not a function. So take note of these things. So it's like when you operate a number on a function, you will get it will serve as a scalar. So you will not get any effect on that number. Okay, so the position operator is the same thing as the position we know. And what these operators does is that they tell us if there are two observables or two things we measured. So for instance, momentum and time. So if these operators are commuting, it means that the more you accurately determine one operator doesn't affect the other one. That is just like what the Hensberg uncertainty stated. Okay, so you use the operators to confirm or to check whether the observable parameters that you are measuring, whether one has an effect or influence on the other. Okay, so if the operators are commuting, if you have two operators and these operators are commuting, in other words, when you take their way of measuring to be zero, then you know that it doesn't matter whichever one you measure first. For instance, you are dealing with momentum and time. So you want to first of all measure momentum of an object that is moving, before you measure the time or velocity and then the position. You want to first of all measure velocity of the object, the same object. You want to measure the position. Then you switch it. You first of all determine the position and then the velocity. Now, if you sum these two approaches together and it is giving you zero, it means that the operators are commuting. And once they are commuting, it doesn't affect your way of measurement. Okay. And that is what the Heisenberg uncertainty stated in our modern physics that we learn. So these are the operators we need to know. We have the momentum operator, we have the position operator, the kinetic energy operator, and then the Hamiltonian operator. Okay. So once we know these operators, we can now go on to talk about expectation values. So you talk about expectation, your average. Expectation value. Now, when you talk about expectation value in quantum mechanics, what it simply means is that you are looking at the average value of a certain measurement that you've conducted or you've done. So let's say you have a little dust and then you throw the dust 5 times. Now you want to see what is the average value you get upon throwing the little dust for the 5 times. Okay, so the value that you get is going to be the expected value you get, or the average value you get is going to be the numbers that you obtain from the throwing. So your first throw, did you get 0? Did you get 1? The second throw, what value did you get? Then you sum all of them together. Then divided by the number of times you throw the dust. And that is what you call an expectation value. That is an average. Or in better, we send it to the classroom when you want to find an average score of a student. So all the courses that the person has done or the student has done, then the scores that the person has, you sum them together and divide by the number of subjects or courses that the person did. And the value that you get is what we term as the expectation value. So expectation value is nothing but just a mean or an average. Okay. So you take note. Okay. So since we know what it is, or based on the explanation, we can write it. X bar is the expectation value, and this one can be defined as x is equals to the sum of x. So let's say we have x1 plus x2 plus x3 plus up to the number of throw that you have. Then all this will be divided by, don't do that. All this will be divided by, teacher, be divided by x1 plus x2 plus, this is 3, x3 plus up to xn. Okay, so that is how you find your mean. Then we can now put them in a summation form. So x bar will be equals to, so when you sum the denominator together, it will give you a number. So you can take that one out. So you can have 1 over n. Then you are summing from I is equal to the first throw to the total throw that you have, so n, and you will now have your value as x I f I. Okay, that is if you have a sum. So here our n is equals to the sum of the outcome. So that is going to be your x1 plus x2 up to your xn. So that is how you define your expectation value, where the I starts from the first number or the first row to the last one. Okay, so if you want, you can put the sum here. Since we are adding, you can just take off the x1 plus x2 plus x3, and then you write your summation as this. This one can also be written as to be equals to 1 to n of x. So you can also write this one here. So this signifies that you are summing. So let's now bring it to the operators. If you want to write it in the form of an operator. So let's say if we have an expectation value in terms of a quantum mechanics, you want to find an expectation value of a variable. So let's say you want to find A. A is your expectation value. So this is the way we write an expectation value. When you see any variable in a square, in a triangular bracket, it means expectation, or it is talking about average. So if A is a variable or a letter, then we want to find its expectation value. We let A is equals to the integral from negative infinity to infinity, and then you write your function in the conjugate form. So let's use a wave function, which is a function of x. Then we have our expectation value being sandwiched between the functions. So this would be psi of x and then the x. So where A is our expectation value, is the expectation value. In other words, your mean value or average value. Okay, so when you see it in an integral form, it means that you are looking for the average of A. So take note, psi star is the conjugate form of the wave function psi, and we know what the conjugate means. So the conjugate means that it's the complex conjugate. So you negate the complex part of the function, any function that you have. So let's say if your psi is equals to maybe 2x plus iy, then for you to get the psi conjugate, which is a complex conjugate, this one will be equals to 2x minus iy. That is why you will get the complex conjugate form. So if your psi is equals to 2x plus y, then your psi conjugate is the same thing as 2x plus y, because this has no complex part for you to negate. So when you take a complex conjugate of a real number, then it's still a real number. So before you can have a complex conjugate being changed, then your function should comprises of a real part and then an imaginary part, so that when you now take the conjugate of that function, then the imaginary part is going to be taken as a negative. So this is how we write it. So let's say we have a displacement or a position which we want to find the average. So this will be equals to the integral minus infinity to infinity. Then you have your psi conjugate of x. Then you have psi, the x, you bring the expectation value, so x. Then you will now have the real part of the function. So this one in terms of x. Then the x. Okay, so we can write this one as that. So let's say in the momentum you want to find the expectation value for a momentum operator. So for a momentum, the expectation value is written as this. So you have your P in the triangular bracket to be equals to the integral minus infinity to infinity. Then you have your psi conjugate of x, that is a function of x, then multiplied by the P. Then you have let me put this one cap because this would be an operator. Then you have your other wave function, which is a function of x dx. Now you have to, you see, this momentum is an operator. It's not like the x. You see the x, when I wrote the position operator, when I operate that one on anything, I will still get x. So that will going to be like a direct multiplication. Like if I multiply 2 by let's say 2x, it's going to give me 4x, right? But since this is an operator is in a form of differential. So you can't say d on the x of 2 is still 4x. You can't do that. Okay, because the momentum operator is now operating on the function, not multiplying by the function, because the position is just a scalar. So when I multiply a scalar by, is just the factor will going to be increased by that function. So this is 2x, you multiply by 2, you get 4x. So it is the factor has been increased by 2. But 2x, you operate on 2x, this will give you 2, but not 4x again. So that's why you should know how to express your operators, or which variable is an operator and then which one is just a normal multiplier or a scalar. Don't do that. So when you come here, I can now rewrite my momentum operator, since I know that my momentum operator is defined as minus I h. Then I will have my d. I'll have my d dx. Okay, so this is the momentum operator. You go and substitute it here, and you will now write the p as this: minus infinity to infinity psi of x. Then my p will now be written as minus ih d on the x, then on psi of x. So again, the psi conjugate of x has nothing to do with the operator. Remember I said operators, they act to the left of the function. So you only operate this one on the real part of the wave function. Okay, so it means that you're going to expand this one by taking the differential, but you don't apply that to the conjugate part, because the conjugate part is written before your operator. So your operators act to the left of the function, not to the right. Once it is to the right, it means that it's just a multiplier. It's not operating on. Okay. So let's say we want to find the expectation value of a certain function. So let me put the question was, so find So example, find the expectation value x x find the x of the operator. Okay, so if psi is equals to square root of 2 on L, then multiply by sine in bracket 2 pi x over L. Okay, when or with n is equals to 2, and then x lies between 0 and then L. So x is less than L, x is less than 0. So now this is a question before us, and our aim is to find the expectation value of x. So you first of all define your expectation value expression. So our expectation value of x will be equals to the integral of minus infinity to infinity psi of x conjugate of x, then multiply by x, then psi of x dx. Now this is the general expression, and in your case you are given the limit of integration to be 0 to L. That's why they said x lie within 0 and then L. So your negative infinity to infinity will change to L to that, and again the third is at n is equals to 2. So it means that you are looking at two possible ways. Now your second thing is that you will define your conjugate. So psi is given as this. So your psi of x is defined as square root of 2 on L sine 2 pi x over L. Then what would be the conjugate of sine of x? So since this is a real expression, it will still be the same thing. You are not going to change anything. So this will still be square root of L, 2 on L, then sine in bracket 2 pi x over L. Now, after you define your wave function and its conjugate, you send it back to the general expression of the expectation value. Then you substitute your limit. So we are now coming to substitute psi and psi conjugate into equation star star. Yes, is somebody hands up? I got an alert. If your hand is up, please, you can go ahead and then ask the question. Okay. Probably somebody that hesitate or join. Okay, so let's plug in psi and psi conjugate into the function. So in that case, we are going to have our expectation value of x to be equal to psi. Now our limit is 0 to L. Then we have root of L on 2, root of 2 on L, not L on 2, root of 2 on L, then sine to bracket 2 pi x on L, then we have our x, then times the same thing, root 2 on L, then sine in bracket 2 pi x over L, then the x. Okay, so you multiply. So by doing that, we have our expected value to be equals to, we can take the constant out. So square root of 2 over L times square root of 2 over L will be only 2 over L. So we can bring that one outside the integral because it's a constant value. Now integral of 0 to L. Now sine theta times sine theta is sine square theta. So it means that this is going to be sine, but we have x here. So let me bring the x before. So we have x, then sine theta times sine theta will be sine square theta. So this is going to be sine square, then 2 pi x on lambda, then the x. So we will now integrate this. So if we integrate this, we will use the identity sine square theta. This one you can go and do it. Sine square theta is equals to 1 minus cos. Okay, I'm using theta. So 2 theta all divided by 2.
Okay.
So everything here divided by 2. This is an identity. So instead of you, so in this case, our theta is defined as 2 pi x over L. So instead of we using sine square of whatever we have, we will remove the sine square 2 pi x on L and substitute 1 minus cos 2 multiplied by 2 pi x over L divided by 2, and we do the integration. So let's do that here. So this is just an identity, and I'm saying that in our case, our theta here is nothing but what? 2 pi x. So our expectation value here will now be equals to 2 on L, integral of 0 to L. Then we still have our x, but the x is multiplied by the sine square theta. So we open bracket, we have 1 minus cos, instead of 2 theta, we'll multiply by it. So 2 times 2 will give us 4. So that's going to be 4 pi x on L. Then everything here is divided by 2. So I'll bring my divided by 2 here to show that it is divided by all the words in the bracket, or all the numbers in the bracket. Then the x. So if we expand, I can actually factorize the 2 out too. Okay, if you want that, you can take this 2 out and you come and cancel the 2 here. So you now leave 1 over L. Then you have x of this, and then that. Then we do our integration. So when you do that, we're going to have our expectation value to be equals to whatever we have there. When we simplify, we'll have it to be 2 on L times L square on 4, L square on 4. And everything here simplified to be L on 2. L on 2. I will explain this. So why we are getting that is that, you see, here we have cos here. Now, when you integrate cos, you will get a sine. So, but sine is what? An odd function. So you see that the part that had the signs will go to 0. It will converge because we first of all saw that sine is an odd function and it is a periodic function. 2 pi, if you take pi, sine 0 is 0. So this is not a pi, but 2 times pi. So 2 pi is what? 360. So sine 360 is 0. So 4 pi, that's 360 times 2. Sine 720 will give you 0 in that order. So you just ignore the sine part. Then you will be left with it. So whatever that will be left here will be x times 1 will be x over 2. So when you integrate x on 2, this is what you are going to get. So like what I'm saying here is that this part will automatically go to 0. You don't need to worry yourself about it, because when you integrate the cos of whatever that is here, you get sine of it, and the sine will make it converge. So it will make it sum to 0. So you just ignore. So you pick the first term. So this is going to be x times 1 will be x on 2. When you integrate x on 2, you get x squared over 2. So when you have x squared on 2, we now put our limit. So if you have x squared on 2, so okay, let me take it from there before I come to write this down for you too. So I'm saying that we have this, then when you integrate whatever that is there, it's going to be x squared on 2. Let me see. On 4 rather, because there's 2 here, by x squared, the 2 will come down, so it's on 4. So x squared on 4. On 4. Now our limit is from 0 to L. So wherever we see x, we put L there. So this will give us our 2 on L, this outside, then multiplied by x, which is now L squared, then over 4. So L will cancel one of the L's here. You will have L2 into SL1, 2 here will give us 2. So that gave us the L on 2. So your expectation value for that expression is nothing but L on 2. Is that clear?
Yes, sir.
Okay. Sir, wait there. So can you go over this one because over here now.
So which part? Which part should I start?
So with the integration up there before we arrived here, at where we had the x equal l and go back. So go back and
Okay. Is it here or has to go forward or
no. Slide 7, slide 7.
okay 7? 7 talks
Good.
about the
Sir.
operators. Yes, here.
I don't know. Sorry. Yeah, this part. That's slide 8. Yeah.
Let me come.
So
I think
yeah.
my okay. I thought like it has changed, but that's correct. Okay. So slide 8. Uh-huh.
Yes, sir.
So
So it seems,
yes,
yeah, if you can go over this side for me, sir.
but
Okay.
do you understand the general expression of the expectation value? You got that one right.
Yes, sir.
Okay. So in our example, the example is that find the expectation value x if the function, that's the wave function, is defined as this, with n is equals to 2, and our x, that is the position, is depending on 0 to L. So this means that this is talking about a confined well, a well that you have it being bounded or something like this. So if this is a well, now you have 0 to maybe a potential. Okay, this is a potential here. So it means that you are being bounded. Talk about bounded,
Hmm.
means that you are within your own.
Uh, Japelo. Okay, you're going to now. Don't go.
Please, please, Francis, is that Bismarck? Mute yourself.
Please mute your mic. So
Okay, so this is like a well, and you are trapped here. So your movement is only in one direction. So you're moving along the x like this. This is only the possible way you can move, front and back. So you are moving like an oscillator. Okay. So now that is the meaning. So your starting point is 0. and then your final point is L. So the L is nothing but they're just looking at the length of the well. So here, so that will be your boundary. So your first and then the last boundary is your definite integral. Now we substitute the expression of the wave function into the general expression for the expectation value. And since this expression has no conjugate complex part, sorry, when you take the conjugate of it, it will still be the same thing. Just as we saw in our previous lecture, we said when we take a complex conjugate of an imaginary number, it will be negative. Or when you take the negative, this one times it function, this one will give you C absolute. We saw this one. I think the last lecture or the last two. So this is what you have now. When we substitute our function here, we will now integrate, use the normal integration that we know. So this is our normal expression. This is our conjugate format. Then we substitute it to the expectation value expression. Then this one will be our psi conjugate. Then our expectation value is there. Then we have the real part or the conjugate part. Now we will multiply through. We have root. If you have square root of x times root of x, that will give us root of x squared, and this is going to give you x. So the same thing that we did here. So 2 over L square root times root of 2 over L. The root will cancel, leaving 2 over L. And this 2 over L is a constant. We take it out from the integral. Then we said sine square has a relationship with this. So when you take sine square theta, this is an identity. It is the same thing as 1 minus cos 2 theta, all divided by 2. So this is an identity you should know. It can be proved from first principle, but we are not after these things. Okay. So this is for math. We are doing physics. We only need to use it. So this is how I should have. I would have gone straight. I would have gone straight to write the L on 2 there. But if I do that, it will be more complex for some of you. So that's why I said, so we relate it with this identity. Then instead of we integrating sine square to sine square theta, we'll substitute this one so that we can have a simpler expression to be able to do our integration. So that is what I did here by replacing this. But here, so since I'm using theta, but in our case, our theta is what? 2 pi x over L. So that's why I say, okay, our theta is equals to 2 pi on x. So whenever I have theta in this expression, I'll put 2 pi x on L there. So when we come down here, I can factorize the half out. So if I take one half out, I'll have 1 over 2. I'll multiply by 1 minus cos in bracket. There is 2 already here, but I have 2 pi x here. So 2 times 2 make it 4 pi x over L, then the x. Now we integrate. But so here that I was saying that because this is cos, and you know, when you integrate cos theta, the integral of cos theta will give you sine theta. Okay, then when you differentiate cos theta, that will give you negative sine theta. Now, we saw from the last lecture that sine is what? An odd function. It's odd. And then cosine is an even function. And we saw that even times even will give you even, odd even will give you odd, odd will give you even. Okay. So since this is an odd function, you just forget about that part because it's 2 multiplied by pi. So it's a factor multiplied by 5, and you know that this is going to be 2 pi is 360. You multiply by 2 again, you get 720 because it's periodic. By 2 again, that will be 1440. If one pick your calculator and type all these figures and see, it will always give you 0. So because you know that this part is converging, you just ignore it, forget about it. When you integrate and substitute the lower and upper limit, it will give you 0. So that part of the integral will be 0. So you just ignore that part. So now with that idea, we just ignore this part. We ignore this portion because at the end of it all, it's going to give us 0. So we don't worry ourselves. Then our concentration should be on 1. So now the x will come and multiply the, so like here, what will be left would now be, it will now be like this. Our expectation value will now be 2 on L. Then integral of 0 to L, we have x on 2.
So please, if you can change the
Then they
color of the
multiply
pen.
by, you multiply by the x. So when you do that, you will get x expectation to now be equals to 2 on L. Then this will now be integral 0 to L. Then it will give you x, the x on 2. Then how do you integrate x dx? So you square, you add, so x is raise the power 1, add 1 to it, then divided by the new power. That's 1 plus 1, 2. So this gives you x squared on 2. So whatever you have here will be equals to 2 on L. Then you now have x squared. This is already 2. So 2 times that 2 will be what? 4. Then you have 0 to L. Then you substitute your upper limit and lower limit. Again, because the lower limit is 0, you don't worry. Always the substitution of the upper limit minus the lower limit. But the lower limit is 0. So that part also goes to 0. So you just substitute only the upper limit part. So this is going to be 2 on L times. So wherever you see x, you put L there. So L squared over 4. Then you simplify. This one will be nothing but L on 2. So this will be the expectation value of the x if you use that definition of the wave function. So if you don't understand after the class, just revisit your integration.
Thank you, sir.
Okay. So the energy can also be expressed in terms of the expectation. So if you also want to write the expectation value, that one too is the same thing. You know, the E that we've seen in the expression that I said is the Schrödinger equation. This is the mechanical energy. And it is an eigenvalue. The eigenvalue is just that it is not an operator dependent. Okay. It's just like a number, a scalar. Okay. So when you want to recall eigenvalue, just relate it to a scalar multiplier. So it's just a scalar value. So if you are writing the expectation value for maybe a ground state energy, so the expectation value for a ground state energy can be written as this. Written as this. So we now have our E in the square bracket, a triangular bracket, to be equals to the general expression minus infinity to infinity. Then we have psi naught of x. Then you have the conjugate form. Then you have your energy, which is the Hamiltonian operator. Then psi naught of x. Okay, that's how you can write your expectation value. Now, when you come, you substitute the ground state expression. So this is nothing but integral of minus infinity to infinity. Then you will have psi naught square conjugate, then the expectation value of the energy from here. So E is equals to h nu on 2. So this is the expectation value. We know that the energy is this, and this came from the wave, the photon, energy of a photon. So E is equals to HF or HC or lambda, and we know that 2 pi F is equals to omega. Okay, then we also know that H bar is equals to, no, H is equals to, okay, don't worry, H bar is equals to H on 2 pi. So when we substitute these things to the H is equals to HF, we'll get the H bar nu. Okay, because this is what we are familiarized with. We know that this is the energy of the photon. Okay, that equation, we are all familiarized with that. So if I replace my F, so it means that I have to make F in this subject, the subject here. So it means that my F will be equals to omega over 2 pi here. So instead of F, I'll put omega on 2 pi. So my E will now be like this. H instead of F is going to be omega 2 pi. But I'm saying that H over 2 pi is what? H bar cross or H bar. So that is how you have this one as the energy of a photon. So the energy of the photon can also be written as that. But now we are talking about the average expectation. So average means half of it. So that is why you see it here as 1 on 2 H nu then psi naught of x. So this 2 is coming because you are dealing with what? Average. So the average of this energy will be this. So this would be the expectation. So when we now take this as a value, as I explained earlier, this is not an operator. We've not seen anything that is operating on the function. So you can write it in other way. So like 2 times 2x is the same thing as 2x times 2. Because it's a scalar, you can change the orientation of the numbers and it wouldn't change anything. So I can write the psi star and then psi before the expectation value of the energy because it's a constant. So if you do that, so my expectation value is nothing but integral of this minus infinity to infinity, the psi conjugate, then I'll have psi all of naught of x, then my expectation value, which I have, is half. So I can write this one correct, the x then times half h nu. But this is nothing but psi star star of x, psi star, psi of x, psi naught of x. This is nothing but this, the integral of psi magnitude, the x here. Okay, so it means that when you take a complex number times its complex conjugate, then it will give you the absolute of that. And this is normalized to what? 1. We saw this one, the x. This one will give us 1. So whatever that is here is nothing but 1. The integral of whatever that is here is 1. So your expectation value will now be equals to h nu on 2. So that is how you find or you prove the expectation value of an energy. So just know that it's what? Half of the expression of the energy that you know. Okay. Recall that expectation talks about what? Mean, average, finding the average value of what? Observables, things that you measure. Okay. And since energy is not an operator, so if they ask you to find the eigenvalue, the expectation value means that you just divide the energy expression by 2. Okay, it's not like any other operators like or a momentum or velocity. These are not scalars, so you can't just divide it by 2. I'm in a class. I'm in a class. I didn't ask you to change anything, so go and do it. So that is it. Any questions so far? Any question? Do we understand?
I want to go back with that thing.
I'm going to remove it. Remove it. Then you did it. Go and do it. Yes. Any questions so far, please?
So let's go on.
Okay.
Continue, sir.
All right. That's fine. Okay. So we can also, so what I mean is this one is what we call the normalized. So we saw it normalization. So this one is normalized to 1. So you normalize it to, it's a function, but when you normalize it, it gives you a value. Okay. So you can also write okay, let me skip this. All right. So let's look at what we mean by commuters. Commutators. And
Sir,
yes,
yeah, so the last calculation we did, we mean to say that the result that we get is the expectation value of the mechanical energy.
no,
Okay.
that one is just energy. So when you take the mechanical energy, it should have the potential part.
You should also have the potential part.
So when you have, okay, let me come. If
Mm.
there's a condition attached to you that it can be the mechanical energy of the system, that is, if the position is 0.
Okay.
So once the position is 0, you know that potential energy depends on height. So
Yes.
once that is 0, you will only be left with the kinetic energy.
Okay.
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 So it depends on the condition that you can say
Condition.
is the mechanical energy. It can be the mechanical energy, but at that point, it means that it doesn't depend on the height.
On the height. Okay.
And if you want to take it in that way, because we are looking at a confined particle which is moving in one dimension and it is what horizontal, then you know that any particle that moves along the x-axis has no coordinate along the y. So
Okay.
height is 0 there. So you
Okay.
can say that it's a mechanical energy
Okay.
from
All right.
that concept.
Thank you.
Yeah, you're welcome. So, and then urgent states. To them. Okay. So when you talk about commutators, as I said earlier on, what they use or help us do is that in this particular context, so if you want to measure two um, dependent observables, so let's say momentum and then a position, so you use the commutators. If the operators commute, it means that when you find their differences, it will give you 0. When you find the differences and it is not giving you 0, so it means that those operators, they don't commute. And once they don't commute, their way of observing is what very important. That is, their way of measuring is very important. So if you take momentum and then displacement or position, then you take the position before the momentum. It should be the same thing as, so like this, how you write them, comma p. If this one minus p comma x is 0, so we are saying that these two operators commute. So this is an operator, an operator, this an operator, this an operator. So when you get 0, it means that they are commuting. But when you do it this way, you are getting any expression apart from 0. So it means that they don't commute. And once they don't commute, their way of what? Measuring affect 1. So, and that will bring us to the uncertainty principle that was stated by Hensbeck. Okay, so that is all that commutators here is talking about. So let's say we consider an operator. So let's consider an operator. An operator P that represents a physical observable. A physical observable of a system. Okay, so that is momentum. So let's say that is P is momentum. That is momentum. Okay. Now, when you have a particular state, okay, the state will talk about the function. So let a state be the wave function psi. Okay. Now, if you now want to write this operator on the side, you can write it as p psi. So that is how you can write. Now, if you also let another operator, let's say q. So let another operator, let's say q, also operate on the same state psi. So it means that the operator will also be written as this. So we said operators, they act to the left of the function. Now, so if these two operators are commute, okay, if these two operators commute, it means that when we take P of psi, it must be the same thing as P of psi. So now if I take P of psi minus P of psi, that should be 0. And this is what will tell me that P and then Q are commutators or commuted. Commutators, let me say commutators. Okay. So how do you write two operators? So if you have operator A and then B like this in the bracket. So let's say this is operating on the wave function. So this is equals to A psi minus B psi, or if you want to take off this, then you want to write it in terms of the two. So A commuting B will be the same thing as AB minus BA. So if this is giving you 0, so they are commuting. So when they're like that, it means that A comma B will be the same thing as B commute A. So this commutative identity, I think we came across it in mathematics. When we are talking about, you talk about the property, dissociate property, associate property, and then the commute property. Okay, so this is what happens. So what the operator seems to do is that, what operator seems to do is that it helps us understand the arrangement of some observable. So which one should be done first? So once they are commuting, it means that that thing that you are observing or measuring doesn't depend on each other. They don't depend on each other. But the fact that they are not giving you a 0 result means that they follow an other way of what? Measuring. Okay, so that is the meaning of operators. Okay, so let's put it in an example form. So our microphone is on. Are you asking a question, please? If you're not asking a question, kindly mute yourself. Thank you. Just a minute, let me add more slides too. Okay, so example. Sorry. So example 2. The example says that show that a kinetic energy operator commutes with a momentum operator. Show that this is equals to 0. Okay, so solution. So the solution is you define your operators. Okay, so T commuting, or for T to be able to commute with momentum, so you have T commuting with the wave function minus P commuting with the wave function must give you 0. Okay. So let me write it separate so that you can see. So this of psi is equals to T of psi. And this should give you 0. So when you solve for it and you are not getting 0, so your conclusion is that it does not commute. If you get 0, you conclude that the operators commute. Now, what is the definition of the T operator? So you write it. So T operator is defined as less h square then over 2m. We saw this earlier. Then the square on the x square. Then your momentum operator is also defined as you have minus IH d dx. Now you substitute this one into the expression here. Okay, so your T operator commuting with P operator will now be equal to, we have the operator of the kinetic energy with the wave function. So that will be minus h square over 2m, then the square over this x square, but this time is now the wave function psi. Then we have an operator sign here, minus. So minus, then you have this, if you want, you can put them in brackets. So minus I h, then d of the wave function psi on the x. Then you close, so that everything should be with there. So when you sum up this, so the left hand side should be the same as the right hand side. So when that statement valid, then you can say that they are commuted. Okay, so when you have that, we will now try to see. Now this is T first, like T has been written first in the square bracket, followed by P. So you simplify that one and then see what you will get. Okay. So let's simplify this one. Right. So this one we're going to give us minus h bar square over 2m. Then the square psi over the x square. Then minus this will give us plus I h bar the psi over the x. So this one is for this. So it means that h of this, comma p of this is given as this. So, oh, I think I've omitted something here. Correct this one. This one is supposed to be like this. This is correct, but I'm supposed to bring the second part. So this one would be the changing of that. So this one will also be the other way. So P, comma T should give you 0. So when you change the orientation, so you see that the first one is T first before P, then the second one is P first before T. So what we did is T first before P. So let's also do for the T first before the P. So the same definition of the P and T, but this time you now have P, comma T, and that's going to be minus I h d x on the wave function. Then you have minus, then this time you have minus 2. So minus h square over 2m, then d square the x then the wave function. So we simplify this. This gives you minus I h d of psi on the x, then plus h square on 2m d square psi on the x square. So this is equation number 2. So this would be great. So this would be P commuting T. And we're now saying that when we put the two together, we should be getting 0. So the first one is this first. So the first one we have minus h square on 2m. Let me check whether I'm right. Yes. Over 2m. Then the square psi on the x square. Then minus or plus I h d psi on the x. Then everything is minus. Minus, we have the square, h square, not the square, h square first. H square, the square psi over 2m. Then this one we will the square x. Then we also have, this one comes first. So I'll write this one first before the other one. But I'll put that here plus because I use the minus for this one. So this one will be plus. So I'll have this I h the psi on the x. Then this one will also be minus I, because if you take plus negative, it will be negative. So I'm putting everything in bracket. So, but I will expand it. So minus I h the psi the x. So you see, this is negative, this is positive. Oh, this is square. Oh. The first part is minus of this, so this one will be positive. This is minus. Because this will be minus and this will be positive. This will be square. This will be square. This will be 2m. And this one will not come. I will not come. So here will be square. Okay. So this is what
I'm going to turn my bicycle.
So you have this. Now, this will cancel out. So this will do away with that. This also do away with this. So which means that P commuting with T minus T commuting with P is 0. And this shows that P and then the operator P and operator T are commuted or commute or commute. This and this commute. So that's the meaning. So which means that when you are looking at these two things, there is no need for you to take the measurement into consideration. You can first of all measure the momentum, before the kinetic energy, or the vice versa. So that is how you check whether two operators are commuted or not. So you can also do that with uh, this thing, position. You can replace one and then put position there and check whether position and momentum commute. So let's do that in the third example to see whether what Hesberg said is wrong or right. So 2. No, this is 3. So 3, we want to replace one kinetic energy with position. So the same way, check whether X operator and then momentum operator commute. Okay, so the same way, you take your X E minus P X should be 0. Okay, so if you put the wave function there, so first of all, do for this. And this will be equals to, what is the operator for X? X operator is still X. So you have X phi minus this one, that's minus H bar D phi on the X. Then you also do for the P1. So P operating on X. So this will be H psi on the X. I think that there is minus in the momentum differential, so this one will be plus. Minus, minus. So this will be plus, and this will be minus. Because the momentum operator is this. Minus IH psi on the X is the differential for the place. So since this is minus, minus is here. So minus become positive, but here there's no minus. So you have this, then minus. So this is minus. Now you have X of psi. Okay. So when you have X of psi, look up. Yeah, we are missing something here. This is the second one. The operator is, yes, I'm missing something here. So here we are operating the operator on this, and then the function is stuff. Okay, so this is how it is. We'll have X psi. So if you operate this one, minus I H D on the X. When you operate this one is like a product. You expand because this is a dependent of X. So it's going to be this, the X, that you hold phi the subject as constant. Sorry, you hold phi as the psi as the subject. Then you operate on only the X. Then when you come to the second part, you also hold X as constant and also operate it on the wave function. So that is how it will be. Okay. So the first one, since the operator is to the left of the file, it only function or work on the file. I don't know whether you are getting what I'm saying. Did you get what I'm saying?
Yes, sir.
Just a minute. Let me connect this. Okay, so let's take it again. So let me put this one here. So this will be x of psi minus p of psi. Okay, if I have this, then this one will also be. So let's now look for this. Let's look for this expression first. I think that will be clearer to us. Okay, so we'll now define our operator. So x is operating on this. So this will be x of psi minus IH. Then you have the psi on the x. This is what you have. Okay, so it will also operate. No, I'm not saying something. Let me check something first. Okay, we take P of Q minus Q of P to be 0. Yes. So that one is correct. So psi of x of psi minus this to be 0. Okay. Okay. So let's apply that. So here we are omitting this. All right. So let's leave this one for the meantime. Then let me try with this and let's see. P commuted x operator of psi. So this also be P of psi, and then that will also be x of psi. So this will be minus IH d of psi on the x, then minus x of psi. So when we add these two together, and from the definition, we are always saying that the commuters of these operators minus x of p operator should be 0. So let's see if we get that. So now x before the p is this. So it depends on whichever one you bring first. So if we are considering p of this first, so it means that we have minus IH the psi on the X minus X of psi. Then this should be minus the top one that we have, which is X of psi. Then minus this, so minus become positive, so plus IH the psi on the X. So we'll have this being cancelled this. And this will give us 2 of psi. That will give us 2 of psi.
One that will be 2x5. Negative 2x5.
Okay, so negative 2x psi, yeah. So negative 2x psi. So once we are still having a number instead of 0, so we can say that the two operators are not commuting. So their order of measurement matters. Okay, but in the model they're having minus h of psi. We are using x commuting with p. Yeah, the same that they use. So that's what they are getting. So minus IH of psi. So the minus sign actually can come in. You know how to get a minus sign, but where the H bar is coming in, that I am not convinced. Okay, I've seen what they just did is that they made the operators. They only operated on this tree without using it. So what they did is x comma p operator psi. So first of all, you operate the x on the 2 and also operate the p on that one. So like how we saw the expectation value. So this would be x p operator on the wave function. That's the first part. Then when you come to the second part, minus the p operator on x and then psi. This is what they did. So when you do that, you have x, then this will give you minus IH, then d of psi on the x, because this is an operator. Then minus, when you come here, this will be an operator, so it's minus minus. So minus I d on IH, minus IH. So d on the x. Now here you have x and then psi. Okay, you follow the product rule. So this would be x minus x I h, so d the psi on the x. And this will be minus in bracket. Let's follow the product of differentiation here. So we'll keep x as constant and we differentiate psi. So that would be x. Then we differentiate this one respect to psi. So plus, but it's negative here. So negative, negative, plus will be negative. So minus. We also IH, we also keep the phi as constant. Then we differentiate the distance, the x. So the x is 1. So the x is 1. And here will be psi. We put this bracket there. So here will be minus x IH the psi on the x minus. So whatever that here is what is going to be minus. So minus become positive. So plus. So I'll have I x h. Then I'll have the psi on the x. Then minus also make this one positive. So plus. So you have I h. Then this x, the x is 1. So you are left with psi here. So this is negative, positive, they cancel out. And the X commuting P, X commuting P is nothing but I H psi. So this is what they are in the model. And because here is not given as 0, so you can say that X and P are not commute, or do not commute. Let's say do not commute. Do not commute. So this is what we check it as the uncertainty in position time the uncertainty in the momentum is greater than h over 2 pi. Okay, so that is the meaning. So once they don't commute, it means that the change of one affect the other, or the order of measurement matters. So you can conclude by saying that since the uncertainty in their position affect the accuracy of P or momentum. Okay, so that is that. Okay, so we also have the matrix element of a linear operator, how we can write the operators in a matrix form, and the same thing as we saw last week in the linear operators, how to write a linear operator in the matrix form. So in the same way, so when you have okay, let me write matrix element of a linear operator. So operators can be expressed in the matrix form as this. So if A is a matrix, and then this matrix is defined as this AI J. The I and J signifies the row and then column element of A. So I takes the row, J takes the column. So when you see like A, I, 2, which means that the element within matrix A, which is found in the column 1, and then row 1 and then column 2. So for instance, if I define A as this, A is equals to 2, 3, 4, 5, 6, 7, and ask you to identify A, 1, 2. So this is what you do. The first row is 2, 3, 4. That's the first row. Now first column is 2, 5. Second column is 3, 6. Third column is what? 4, 7. So you want the element that is in column 1, in row 1, but column 2. You understand? row 1, column 2. So if you do that by crossing, so this is your first row, then column 2. So this is column 1. So C1, C2, C3. So where it will intersect, that's the element here. So you see that your A12 is nothing but 3. So that is how you use it to identify the element within the matrix. So if you are asked to find A, or somebody asks me to change the color. Sorry. So you're able to find let's say 1, 3. So A13 will be nothing but what? 4. So A13 is 4. So 4 is in row 1, but column 3. Okay. If you are also finding A21, so it means that row 2 element, which is having column of 1, so that would be 5. Okay, so when you write it like this, they have meaning. So A, J, A, I, comma J means that you are taking I for the row element and then J for the column elements of A. So this can be written as this is equals to the expectation, or no, the ket of phi I, then we bring the expectation of the matrix A, and then the ket of it, then we close. Okay, then where I, J is equals to 1, is equals to 1 to N. So 1 to N. N signifies the number of matrices that you have. Okay, so this is how you also write the operators in terms of matrix element. So when you also find the matrix element of the operators, and then it gives you a variable or a value other than 0, so the same way you conclude by saying that the operators are not commuting. Okay, so that is for operators. Any question, please? Do we understand?
Sir.
Yes.
No, please, it is stop presenting or network. I think the network is having a network problem.
So Festus has lights out over this place, so he's trying to join us with his phone and also to see if the network is strong enough. So let's just be patient, okay?
Hello.
Yes, sir.
Okay, you can hear me, right?
Yes, sir,
Sorry,
please.
I just had the lights out, so that's why I was offline. Okay, so let's see. I'm trying with my phone, and I don't know whether the internet will permit. If it will be stable, then we can continue. If not, probably we have to pause and then come back another time. Okay, so I was asking whether there is some clarification or we should move ahead to the next item. Okay. So the next thing we'll be talking about is the Schrödinger equation. Is the Schrödinger equation. Makes my writing slow. Schrödinger. So this particular equation that we are talking about is the fundamental equation in quantum mechanics. Just like when you talk about Newton's second law in the classical mechanics. So the Schrödinger equation also play a fundamental role, and it tells us the probability of finding a particle within a system at a time. So you say like when you know the mathematical information about the system, that is the wave function, when you know that one and you try to take the probability of that, then and able to double that, okay, then the probability of locating the particle is high, or the chance of getting the particle is high. So when you take the square of it, then you have something like a dumbbell shaped like this. So wherever you have the maximum of the curve will tell you that, okay, in that range, locating the particle is higher than the extreme, that is the end part. Okay, so that is what the equation is about. So we will get to understand it better. So this equation is in two aspects. We have what we term as the time dependent Schrödinger equation, and then the time independent Schrödinger equation. So when you talk about the time dependent, as we know, whatever, whenever we are dealing with something and we are putting time as our reference, we are looking at as time passes, what happened. So it means that we can express the equation in relation to time, and we can also express that in terms of only position or displacement. Okay, so the general expression for the Schrödinger equation is what we saw earlier as the Hamiltonian. Okay, so the Hamiltonian of the wave function is equals to the eigenvalue or the energy multiplied by the wave function. Okay, so let's write something small under this. So we can say that the Schrödinger equation is the total energy of a body that is okay, so let's take it from there. So let's take it from the kinetic energy point of view. So if you have the kinetic energy, since we are saying that the Hamiltonian is equals to T plus V. Now we define our T as half mv square, and this is nothing but p square
Please,
over
sir,
2m.
sir, your screen is not showing me.
Like
Yes,
seriously?
please.
Wow. No, but I've shared too. Oh,
Yeah, please,
Yes,
it's not
at
showing.
was showing, but now it's not showing anymore. So I think it's maybe your network.
that's serious. Okay, just a minute. Let me see. Hello, check and see whether it's showing at your end now.
Yes, please, it's showing.
Okay, thank
Yeah,
you.
it's not showing.
All right, so as I was saying, so this is the expression of the mechanical energy or the Hamiltonian expression. So we have this. So we can define the kinetic energy in terms of velocity and then as well as in terms of momentum as this. Now our potential energy, so our PE, which we normally write as VE, V as a function of that. So we can also have this. Now to now sum up our mechanical energy. So our H is equals to P square over 2M plus our V. So this is our total energy of the system, which we call the mechanical energy of the system. Okay, so I don't know whether we'll be able to reach here in terms of the classical mechanics, but you will see similar thing where we'll be talking about the Hamiltonian equation and then the Lagrangian. So the Hamiltonian is just a sum of the kinetic energy and then that of the potential energy. But when you come to the Lagrangian, that will going to be the difference. So the kinetic energy minus the potential energy will be the Lagrangian expression. So if we are able to reach there before, I think tomorrow and then maybe any other day that will be freer. Okay, so that is it. So we now have our total energy. Now we can write our energy. So don't be confused with the H and then maybe the E. They're all talking about mechanical energy, total energy. But this is the Hamiltonian. Okay, once you are dealing with the operators, you use the Hamiltonian operator to tell that the operator operates on the wave function. But when you just use the mechanical energy straight, it doesn't mean that you are wrong, but the E just tell you that the eigenvalue of it. So that one, it is not written in terms of what operators or as an operator. So we can write our energy of the system if you use the E. So the eigenvalue energy of the system is E is equals to the T plus the V. Then since we are dealing with like photon, so this would be H nu will be equals to P square for 2m plus V. So that would be our energy. Now, from the de Broglie wavelength, we also know how momentum and then the wave number and then these are also related. H bar, K, and then lambda. We know how these two also related. So we can write it in terms of the wave number. So H mu is equals to, so P is equals to this. H bar K. We saw this one. So this is our P. So instead of this P, we'll put whatever that is there. So this will be H square K square over 2m plus our potential. So this is another form we can write. So if our potential is now 0, so in the case that the potential is 0, is that we have P to be equals to 0, it means our H of nu will be equals to H square K square over 2m. So it means that the particle is confined within a potential well. Okay, so a potential well, there are places that you have the potential energy to be 0. So once the potential is 0, you only the system will be purely kinetic, or you only have a kinetic energy at that position. So you have your energy expression to be this. So if we now consider an arbitrary function, which is a wave function, so let that arbitrary function be the wave function. So we have psi, which is as a function of position and time, x of t, that should be equals to a raised to the power, the wave format, which is I into bracket kx minus omega t. Okay, this is a progressive wave equation. So when we learn this now, since we have differential for our operators, when you look at the H operator, we have the square with the wave function. So we have to differentiate that to obtain the second differential. So when you do that, we can differentiate this one, the wave function that I just defined as this. So let's find the first differential. So for me to differentiate my psi, so d of the x of psi of x of t, this is going to be d on the x. Then I have my a e to the power minus I in bracket kx minus omega t. So this time I'm considering only x. So I'm not looking at the time. So it means that the t part will be treated as constant or 0. So, and whatever that is raised to the power is nothing but this. So e to the power minus I kx then times e to the power I omega t. This is what is there. Okay, so if you expand this, you'll be like this. So we forget about the time side and we differentiate this. So this will give us a. Then this is why we are differentiating respect to x. So when you differentiate kx respect to x, we are left with k. So the k will come down here. But it's negative, sorry. So this negative I will come down. Because when you expand it, you get a negative I. So that will be minus I k, then e to the power minus in bracket kx minus omega t. So like this, let's assume that you are differentiating this because you will keep this one as constant. You keep this term as constant. So you are differentiating only this. So how do you differentiate it? The other time I show you that if you have e to the power theta and you are differentiating, it's the same thing. But let's say it's a certain factor here multiplied by the theta. So that factor will fall down and you repeat the differential itself. So this. Okay, so now we are differentiating e to the power minus kx. So it means that we have to multiply by negative I kx, then repeat whatever we have. So that's why minus I kx, this a is what was here. So it's the same thing. But we are now multiplied by I k. So minus I and then the k, then we repeat whatever we have. So that's how we differentiate it. So this is the first differential. So to go for the second differential, so that was going to be d square on the x on whatever you differentiate first. So this one now will be psi again of x of t, and that's going to be d dx square. Then we are differentiating minus I a k e to the power minus in bracket kx minus omega t. So this is what we will differentiate again. And when you do that, you have negative coming down. There's I here, please. So when you do the differential again, following the same formalism, so minus I. So now this time around, you have minus to make it positive, but the I will become square. So you have I square. Then and this A will remain this stuff. Then the K.
Please, your screen is off. Your screen is off.
That will come down and multiply another K will be K square. Then you repeat the function itself. So e to the power minus I kx minus omega t. Then this my network is better. We call the class. I don't know why I have network connection here. It is showing us.
Back. It is back.
It's connected. I don't know why.
It is back now.
So it's back. It's back.
So it's back, man. It's back.
Thank you. Thank you.
Off
It's
again.
gone.
Okay, so
Asamba.
Now Travgita.
okay. So let's manage and see whether it will be stable. Okay, so this is what we are going to have. So this now be our second differential of our wave function that we define. So let me just write the wave function psi of x and y. So x comma t. Okay, so the reason why we are doing this is that, you know, when we express our Hamiltonian operator, you see that we're having the second differential of the wave function. So we do that and then substitute. So whatever we are doing is, the idea behind is that we are trying to prove or arrive at the Schrödinger equation so that we can now deduce the time dependent and then the time independent Schrödinger equation. So if you look at equation star very well, you can see that let's go back and look at the arbitrary wave function that I defined here. If you look at the arbitrary wave function I defined, it's what? A e to the power, is it minus I or I? It's I, no minus. Okay, so this is correct. So we have this one there. Now, by comparing to what we have there, so this should be psi. Okay, I think when I came here, I made a mistake. This one shouldn't be negative. This one should be positive, not negative. Negative. So if it is positive, nothing will change. Just that the sign that is going to change. So at the end of it all, so here wouldn't be negative. Here will still be positive. But our final expression will now take negative. Okay, so now square root of I is minus 1 from a complex plane. So you have root of minus 1 is nothing but I square. So since I have I square here, I'll just remove the I square there and then put my negative 1 there. So this, take away this. So that's minus 1. So please let me go over here with you before, because I've taken out the minus. So this one will be I kx of that raised to the power this. Okay, the second one will be I square. So this will be I square. And I square is equals to minus 1. So in place of this, we just put minus 1 there. So this will be minus 1. Okay, so that's negative. Let me just write negative. Okay, so we now have this. So this is the second differential of the wave function. So when you now look at the wave function that we defined, we see that the first one is a e raised to the power whatever that is there. So if I rewrite this one as minus k squared, then I have a e to the power I in bracket kx minus omega t. So this is nothing but the wave function that I defined here, the arbitrary wave function here. So in place of whatever expression that I have there, this one, I will remove it and I'll put this one there. Okay, so what we had is the square of psi on the x square is nothing but minus k square then psi of x of t. Are you following, please? Have you gotten what I've written on the board? Okay, so if I also take the wave function and now also differentiate with respect to time, because it's both position and time dependent. So if I also differentiate psi as a function of x with respect to t, then divided by dt. So this is nothing but d of dt, open bracket, I have a e to the power I in bracket kx minus omega t. So similarly, my x part will go to 0. This time around, I'm also looking at the t type, the t part. So my x part will go to 0. So it means that whatever that is here will be left with e to the power minus I omega t. So this is what I'm now differentiating with respect to t. So the same way, the factor that is multiplied by t up here will come down and multiply. So minus I omega down to multiply. So the first differential will be equals to minus I omega a, then I'll repeat the function itself. I in bracket kx minus omega t. And this will be my first differential. So the psi of x of t on the t. Then I will do for the second differential. So, but when you look at the full expression of the Schrödinger equation, it's only the displacement part that is being differentiated twice, but the time part is just a one differential. So just a first derivative. Sorry, just a first derivative. So this one is enough. So when we also check, this part is nothing but the wave function that we define. So I can say that my first differential, which is the psi on the t, is nothing but minus I omega. Then I'll put my psi as a function of x and then t. So we are now going to use these two expressions to actually come out with the Schrödinger equation so that we can express it
Sir,
in terms of, yes,
please, why the assumption
yes.
of differentiating the time with just once, but the displacement twice?
So the time is one because when you look at the formula, when I write the final expression of the Schrödinger equation, you will see and you understand why. The
Okay, all right.
second differential of the time is that you're going to make it 0. So you make it like independent of time, because whatever measurement they did is only with respect to the time one. So once you make it twice differential or the second derivative, it will be 0. It wouldn't be
Okay,
time dependent again.
all right, sir. Thank you.
You're welcome. So we'll now have these two. Let me also put this one in the square bracket for you. So here, so this will be the square of x of t, the x. So I will use these two expressions. Okay. So when we move on, now we will now put these two into our equations. But before we do that, let's first of all multiply by h squared over 2m. Because of this, you see, we wrote this. This is just the condensed form of the Schrödinger equation. And then when we expand this using the operator, we have this one minus h squared over 2m. Then we have the square psi over the x squared plus the v part. So multiply by the wave function to be equals to the e, which is a h nu, if you want to write it that way. So h nu of what? Psi. We saw this one. So this is the full version, and this is what we call the time independent. So now, for us to be able to arrive at what we are having, what we have here, if we look at our expression that we have this I new is coming in. We have k square is also coming in. That is a second differential. We don't have a factor of h over m. We don't have the temp here. So what we need to do is that we have to multiply this one by the h over m, so that at the end of it all, we can have something similar to what we are proving or what we are coming to arrive at. So when you are solving or proving at something, you have to be looking at what you want to arrive at. So there are certain variables that you have to force them in. And when you force them in, you don't change the meaning of the mathematics. Because you know, when you multiply anything by 1, it doesn't change the meaning or the number. It's still constant. So you now find a way of doing it. So what we'll do is I will multiply the expression that we have by the h squared over 2m. Okay. So we'll multiply that by that. And we also try to multiply the second part, that is the one we differentiate once with time, by another factor so that we can have it expressed as that. So here, this expression here, oh, my machine is freezing. So this one here will multiply by h squared over 2m. We'll multiply this one by that. I think I should have been labeling my equation. So, but equation star we'll multiply by. So this one, I'm just showing you what we are at. So multiply h square over 2m by equation star star. So it means that we are going to say the second differential. So the second differential, which is the square on the side on the x square. So it's equals to minus k square psi. And this is what we are saying, that we should multiply this one by this h bar square, sorry, over 2m. So whatever you do to the right hand side, you do same to the left hand side. So when we do that, we'll now have our expression to be this. So we have minus h square. We are doing it with this minus this. So this will give us minus h square over 2m, then the square psi over the x to be equals to this. So that will be minus k square h square psi then over 2m. So we have this. Okay. Then psi is there. So we have this one. Then we have to also multiply the other equation 2 also by IH. Okay, we also multiply that one by IH. So let me give this equation. So let's say if this is 1, then also multiply that one by IH. Then that one is it's d the psi on the t is equals to minus I omega then psi. And we're saying that we'll multiply this one by IH. So this would be minus, no, this minus. So IH beside the t to be equals to, we apply II, that will give us minus 1. So that will be minus omega h. Let me bring the h first. So h omega and then psi. So equation 2. If we look at the right hand side of equation 2, this is energy. Now I also come to the equation 1 that we have. So we know that this is a Hamiltonian expression, but this one is equals to what? Energy. You see, from what I've written above the red line, see that this is also energy. So energy can be equated. So if we equate energy to energy, so we'll have, oh, this thing has away, so there's M here. So equating these two, 1 and 2, if you equate equation 1 and 2, equation 1 and then equation 2, so we'll have I H the psi on the t to be equals to the left hand side of this expression, equation 2. This one. So that will be minus h squared on 2m minus h squared on 2m. Then we now have the square side on, there's 2 here. No, I just erase automatically. There's 2 here. So the square psi on the x square. So you have that term, but the psi, bear in mind, the psi is still function of time and then position. So you have that. Now you can leave this one as that, and this will be the time dependent. So it'll be the time dependent. If you want, you can rewrite it by normalizing the I. That is, if you multiply through by I dot I. So you can write another way of it. So that is let me add this v of x. So that's our potential. So this is what we call the Schrödinger equation, and this is a time dependent. So the time dependent is that when you look at the left hand side, it's what being differential respect to t. So that's why we are calling it what time dependent Schrödinger equation. So that is how you prove, or you come out with by the time dependent Schrödinger equation. So equation 3 is the time dependent Schrödinger equation. Schrödinger equation. Okay, so that is the. Now if you are now taking the time independent part. So for the time independent part, we go through the same formalism. That one is just simple. It's just the kinetic part. So that one is just nothing but minus h square on 2m the square psi on the x. So this time you write the function as this. So the t part should be 0. So plus the v of x, then psi of x of t 0 to be equals to e of psi of x of 0. And this is the time independent Schrödinger equation. So actually this solution has no true solution. Even the person that discovered it didn't also even know the meaning. So later on that the equation has been put into use and the meaning has now generated. But stranger, at the time he discovered, he couldn't even interpret, couldn't even know what it was about. Okay, so now if you have the energy to be zero, so it means that this part will be zero. If E is zero, so the whole of that part becomes zero. So you can actually write, since this one is momentum dependent, wave function dependent, you can take it to the other side of the equal sign. So you would do that. So this one now will be the potential minus the energy, then everything in the wave multiplied by the wave function. Okay. Yes, any question, please? If not, let me add some slides and we now look at the interpretation of the wave function. Okay, so interpretation. So one, the solution of the wave function psi is complex. So it's a complex solution. But we came across this one earlier on. We know that when you have a complex number, then you take the conjugate of it instead like taking the magnitude. So that's why when you want to find the location of the particle or whatever you are observing, you use probability because there is no certainty in this. You only have to predict by probability. And when you square it, now it gives you, or it broadens the chance of getting your prediction right. Okay, because when you look at the dumbbell shape that I sketch, so if psi is giving you this, if psi, you sketch psi is giving you something like this. So let's say something like this, that is psi. You see that this is broad. Okay, so your probability of locating the particle is broad and you wouldn't be certain on where the particle will be. But if I square this, it's going to increase this to this. So you now have this boundary. So the probability of getting the particle within here is high because this boundary is what? Short. Okay, so like the particle is moving to and then from. So once the particle is the boundary is closed, so it means that you guess you by all means get the particle within the boundary that you've chosen. But if it is drawn like that, it will be hard to still get it because it will take a longer time to be able to execute this of the wave, the complex wave function. Then it increase the chance of getting the particle that you are observing within that confined unit. Okay, so that is so it's complex, and it is measure of the probability, yeah, probability of the density. Okay, so the density where the particles are being condensed. So density, of course, this implies that the psi magnitude is the probability of finding the particle between x and then x plus the x at time t. So this is talking about interval. So if you started from A to B, this is x. Now this will be x plus change in x within this interval t. Okay, as time elapsed. So that is the meaning. So it gives you a probability. That's what I said, probability density. So it's a probable. But once the density, you know what density means. Density means how heavy it is. So the condensed nature. So the possibility of locating the particle there. But always having in mind that the particle is in constant oscillation. It's not like it rests at a point. You know, it's just moving constantly. So when you do that, so the probability of normalizing this will give you 1. You know, when we're dealing with probability, either 0 or 1 or 100%. So within 1 to 100% or 0 to 1, you will have different options or chances of being true of whatever you are doing or doing. So the second one is that, so the solution for equation for a given function with a potential are possible for many situations, each with a corresponding energy E. This ensures that only certain values of E are allowed. So the second assumption is that this equation talks about quantization. That only certain energy states are allowed. Otherwise, quantization are quantized. Okay. Now the assumption of the equation is that so the third assumption is that the probability density is 1. So when you take the psi x of t, this should be 1, and this I'll call the probability density. Probability density. Let's we'll close at 2. Okay. Am I still online at all?
Yes, sir.
Oh, okay. All right. Thank you. Then the fourth one, any function which satisfies the time independent Schrodinger equation must be single valued, continuous, and then smoothly varying. So for the time independent, the time dependent, independent, independent, the system must be in a single value, a single value, continuous, and then smooth. So varying, then lastly tend to zero as x approaching, and 10 to 0 as x approaching infinity. So the fourth assumption is that the energy of the system for the time dependent independent equation, it must be a single value. The energy must be in a discrete, so at a single value. Then it must be continuous, and then the position will be the energy will be zero when the position is approaching infinity. Then the last one is talk about the normalization condition, where the probability of finding the particle along the chosen one dimension is 1. Okay, so that's the fifth one. So the probability of finding the particle position in 1D is normalized to be 1. So you have this. X is equals to 1. Negative infinity to infinity. Okay. So these are the two ways that we can express the Schrödinger equations. The two, one is the time dependent, the other one is the time independent. And the interpretations are what we have.
Sir,
Yes.
yeah, please, can you throw more light on point 2 briefly?
Point number 2.
Yes.
Okay. The point 2 is that the solution of this equation, that is the Schrödinger equation, shows that only certain energy states are allowed. So when you are looking at the occupation in terms of the quantum mechanics, we have the equation to be En is equals to n square h bar over 8 pi al or something, if you remember this.
Yes.
So I think here is keep or something like that. So this is the energy state. So when you pick one energy level, then you can find the energy that the particle will be having in that particular state. So the state has to do with the energy levels. So the shell. So when you go back with the shell, so first shell, second shell, third shell, and that order. So the energy stages are in discrete. So the first The energy that
Okay, sir.
the come again. Okay, the energy that
Okay, sir, I'm
each
listening,
level.
sir.
Oh. Okay. So the energy levels or the energy that each um, electron or whatever should have to be able to reside in that energy level is discrete. So when an electron is in a second uh, energy state and it needs to make a transition to the third energy state, so it needs more energy. It has to absorb more energy that will be equivalent to that state so that it can reside there. The same way, when you are at a higher energy level and you want to uh, occupy a lower energy level, means that you have to release a certain amount of energy. Then you will now be able to reside in the lower energy level. So that is what it's saying, that when we solve for the solution to the Schrödinger equations, the energy that we'll be getting will be in terms of what? Discrete. It will be in terms of discrete numbers.
All right, sir. Thank you, sir.
You are welcome. Okay, so let's see. We can do something before the you log us on 10 minutes. So 10 minutes, 10 minutes. Okay, so I hope you have your model. So if you look at the first question, said by solving the time dependent Schrödinger equation for a free particle. So a free particle means that it's not bounded. So once it's not bounded, the potential is zero. Find the condition imposed on the angular frequency and the wave number. So you find the condition that is imposed on the frequency and the wave number. So when you have this, say when I'm drawing the potential, well, I think we've not got into this. You may not pick it well. Maybe I will allow it when we get here. So this one can be 1, this part will be 2, and this one will be 3. This I will call the potential world. So now in the case that this is not bounded, it is infinity. So once it is at infinity, so you see that area 1, or where I label 1 and where I label 3, they are outside the well. So whatever that find themselves is to infinity, both to the left of the well and then to the right. But if you find yourself within I, that is inside this container, it means that you will be restricted to move in one dimension. But once you find yourself at where it is, so the potential is zero here, so you will be able to move freely in all the degree of freedom that you can think about. Okay, so that's why you say like the condition that find the condition imposed on the angular frequency and the wave number. So when you are inside the II, so once you are inside here, you'll be only moving in 1D and your potential is zero. Okay, because you are limited to move in the horizontal direction. So when we are doing with the potential world, you understand it better. So the second one is by applying the method of separation of variables, solve the differential equation. So the equation is defined to be zero, and you have a phi there. Okay, so it depends on the definition of the phi. For you to be able to get the zero at the right hand side, It depends on how the phi depends on the variables. So if phi is independent of either x, y, and z, so it means that the phi is a constant. And what is a constant? When you differentiate a constant with any dependent variable, you will get 0. Okay. So on this context, since the phi is not dependent on x, y, and z, it means that you are treating it as a constant. So it's like phi is just a number. So if phi is 2, so if you take d of 2 respect to the x, it should give you 0. Then plus d of 2 with respect to dy, that one too is 0. D of 2 respect to z is also be 0. So 0 plus 0 plus 0 plus 0 will give you the 0. But in the case the phi is defined x and then something, so this will be giving you maybe the expression like 2x plus 3. So in that case, when you differentiate it with respect to x, then that one will not give you a value. Or when you do the second differential, because if you define it twice, you will get 0 too. But they've not defined this one in the question for you, so you will just presume that this is not x and y, or it's not a position dependent. You just make it that way, and then you do your differentiation. That is how you make your assumption. Now the third one is, which of the following function would you recommend as a possible eigenfunctions? So you have in quantum mechanics, you have the first one, psi as a function of x is equals to e to the power minus x squared. Will you recommend that one as an eigenfunction? Please, someone's microphone is on. Is the first one an eigenfunction?
So the model is not with us currently, so
Okay.
yeah,
Okay.
so
Okay. Then sorry for that. I thought maybe probably you having it then.
not
So
the
okay,
model.
but this is what they're saying.
Okay.
You have psi of x to be equals to e to the power minus x squared. So if this is a, this is b. Psi of x is equals to 2x. Then c, psi of x is equals to x e to the power minus 2x squared. And then the question is that which of these will you recommend as a possible eigenfunction? Eigenfunction, which of them is an eigenfunction? But you know what eigenfunctions are. So the first one, is it an eigenfunction or not? Or we don't know.
Step, we don't know. Please, if you can explain.
Okay. So see, when I write h of psi is equals to e of psi. Now, this is an operator operating on a function. So this is a function. So this is an eigenfunction. The operator is an eigenvector. Then when you come here, this is an eigenvalue. Then this is also an eigenfunction. Okay. Now, the question is saying that among these three, are they all eigenfunctions, or are they qualified to be called all of them eigenfunction, or which one is an eigenfunction and then which one is not? Now, when you look at how we define the function is a e to the power I in bracket kx minus omega t. This is how we define. Now the function is having an exponential term with a certain constant. Okay, so you look at these array expression, which one has an expression looking exactly or similar to your wave function, and tell whether that one is a function or not. Okay, so when you look at A and C can be termed as what? Eigenfunction. But when you come to the B is a value. Okay, because this is 2x. So the x, when you operate the wave vector or the Hamiltonian on this, the two times of it, you're going to get 0. So once you get 0, it's a value. It's not a function. The function should not be 0. So eigenvectors or eigenfunctions are not 0. Okay. So that is the meaning. Okay.
Okay.
So when tomorrow tomorrow you have two lessons, or it's only one?
So it's only one.
Then I would
So
like
what?
to change our meeting time, so that
Okay.
tomorrow we also like go to church, because since 3 weeks I didn't go to church. Like I am no more Christian.
Okay. Okay, sir.
So
Yep. That's overtime.
so let's see if we can meet 12, or it will not be good for you.
I think 12 is okay.
Okay. If it will be fine for you, fine. Then I think this week is our last meeting, but I had somebody want to say something. You come in before
I was asking 12 to what time because we have another class at 4.
4 to what, 5 or 6? Or is it
4 to
7?
6.
4 to 6. Okay, no problem. If we can meet earlier than that, fine. If not, we'll do like only 2 hours. Then we'll find another day. Actually, we have to meet again because today would have been our last meeting. But we will still meet before. Next week will be revision, right?
Yes, sir.
Yes, please.
And then the following week is quiz.
Yes, please.
Yes,
An
please.
exam.
All right. And then exams. Okay. And that's fine. So we will still discuss on the revision week. We'll make
Okay.
discussion. That one we are not going to have a lecture. We'll have a normal
Discussion.
tutorial. Then your exam. So even after that, after the quizzes, if there is a need, we can still meet before the final exam. But
All
if
right,
there's
sir.
no need, then I'll say hallelujah. Okay, so God willing, tomorrow.
All right, sir. Thank you.
Yo, thank you too. Bye.
Thank you. Bye.
Bem, bem, bem.